Section: Introduction. In this section, we discuss how transformer-based architectures have significantly advanced in recent years, achieving remarkable success in various fields such as engaging in human-like conversations, understanding images with high quality, generating videos, creating multimodal content, and completing code. These achievements are largely due to the training of these models on vast amounts of data, which has led to the development of large language models, LLMs, that perform exceptionally well in real-world applications. However, despite these advancements, we observe that transformer-based models and LLMs still face challenges in executing planning and reasoning tasks effectively. Previous research has shown that these models often struggle with tasks that require multi-step planning or complex reasoning. To address these challenges, recent efforts have been made to enhance the reasoning and planning capabilities of transformers. A notable strategy involves simulating the human thought process by generating intermediate steps or thoughts before arriving at a final response. Techniques such as chain of thought, COT, prompting, and tree of thoughts, TOT, have been developed, where COT encourages the model to outline the reasoning steps, and TOT explores different reasoning paths before selecting the most suitable one. Despite the effectiveness of these methods in some cases, there are instances where they may lead to suboptimal performance due to issues like self-reinforcement. Moreover, the effectiveness of these techniques can vary significantly across different datasets, which may be attributed to the varying nature of reasoning required, e.g., spatial, mathematical, or common sense reasoning. Our work aims to bridge this gap by training transformers to excel in complex planning tasks. We introduce SearchFormer, a transformer model designed to compute optimal plans in fewer search steps than traditional symbolic planning algorithms, such as A** search, in tasks like maze navigation and solving Sokoban puzzles. Our approach involves a two-step process. Initially, we train a transformer model to mimic the A** search procedure using synthetic datasets generated from randomly created planning tasks. During the execution of A**, we log the computation and optimal plan as a sequence of tokens, which forms the basis of our training dataset. This dataset contains the execution trace of A** and encodes information about its search dynamics. In the second step, we enhance the performance of our SearchFormer model by incorporating search-augmented sequences that include the execution trace of A** and applying expert iteration. This method encourages the transformer to generate fewer search steps while still achieving optimal solutions. As a result, our model effectively encodes a neural planning algorithm within its network weights, capable of finding optimal plans with a high probability and in fewer search steps compared to traditional A** search. For instance, in solving Sokoban puzzles, our models successfully solve 93.7% of test tasks with an average of 26.8% fewer search steps than A** search. To further understand the impact of training data and model parameters on performance, we conduct a series of ablation studies. We compare models trained on solution-only sequences, which include only the task description and final plan, with those trained on search-augmented sequences, which also include the search tree dynamics. Our findings reveal that models trained on search-augmented sequences are more effective at learning the correct search dynamics and generating optimal plans, even with significantly fewer training sequences. This highlights the importance of incorporating A** search dynamics into the training process of transformer models. Additionally, we discover that increasing the number of parameters in solution-only models does not necessarily lead to better performance, underscoring the critical role of the type of training data used in this context. Section Summary. In this section, we explore how transformers can be trained to tackle intricate planning tasks, introducing SearchFormer as a model that outperforms traditional symbolic planning algorithms like a ** search in tasks such as maze navigation and Sokoban puzzles. By employing search dynamics bootstrapping, we first teach a transformer to mimic a ** search and then fine-tune it to find optimal plans more efficiently. Through expert iteration, we guide the transformer to generate shorter search steps while still achieving optimal solutions, showcasing its ability to excel in planning tasks like solving Sokoban puzzles with a success rate of 93.7% and shorter search steps by 26.8% compared to a ** search. Section: Related work. In this section, we delve into how our work differs from and relates to existing research. While previous studies have utilized synthetic datasets to teach algorithms how to reason effectively, our approach takes a unique turn. We aim to enhance the reasoning abilities that are already part of a transformer model structure. Unlike methods such as AlphaZero, MuZero, and alpha geometry, which treat neural networks, including transformers, as a sort of mystery box and apply traditional symbolic planning techniques to enhance the network itself, we take a different path. For instance, these methods might use something like MCTS, Monte Carlo tree search, to directly update the neural network's weights. Our method, on the other hand, leverages the transformer model to create more efficient search patterns and thus improve the model's own capabilities. Here, a planning algorithm is only employed at the beginning to train a transformer model. Other approaches, like Scratchpad, focus on training neural networks using execution traces from reasoning tasks, aiming to predict either the best solution or the best next action. Our strategy, however, seeks to refine LLM-based, large language models, planning algorithms by forecasting the search dynamics of a planning algorithm, essentially predicting the execution trace as the solver works towards the best solution. This is a more challenging problem than simply predicting the best decision-making strategy. Our research also shares some similarities with neurosymbolic systems, such as neural Turing machines and neural programming architecture, which create differentiable architectures that replicate the functions of traditional symbolic systems. However, these systems rely on specific components, like explicit memory units or built-in recursion capabilities, whereas our method, SearchFormer, uses a general transformer architecture. By employing long contexts and positional embeddings, SearchFormer excels at devising optimal plans for a variety of complex planning tasks, marking a step towards developing neural architectures that autonomously learn reasoning and planning mechanisms without prior human input. Previous work has also explored using transformer architectures for complex sequential decision-making in a reinforcement learning context. For example, Decision Transformer predicts the next best action based on a segment of a trajectory annotated with total return values, while Trajectory Transformer aims to learn a model of the world that can predict future states, actions, and rewards. Similarly, Algorithm Distillation trains a transformer to predict the next action based on a segment of trial and error interactions. Unlike these approaches, we integrate the process of how a planning algorithm reaches its conclusion into transformer models. MCTS-Net also tries to learn the search process itself but embeds the MCTS search procedure directly into the neural network, which introduces significant computational overhead and limits the number of rollouts it can handle. Our method, by contrast, can manage much longer search execution traces. We show that transformers can not only mimic a symbolic planning algorithm but also surpass the initial algorithm through fine-tuning. Regarding the problem setup, we focus on two main areas: maze navigation tasks and solving Sokoban puzzles. In maze navigation, the objective is to find the shortest path in an n by n maze from a starting point to a goal without crossing any walls. The Sokoban puzzle involves moving boxes onto designated spots by navigating a worker around the puzzle space, where the worker can only push but not pull boxes, and must avoid trapping a box against a wall. Solving these puzzles requires careful planning since a wrong move can quickly lead to a dead end. The complexity of Sokoban puzzles, due to the vast number of potential box and worker positions, makes them particularly challenging for algorithms like ** search. To generate execution traces for the ** algorithm, we manipulate two sets of nodes: a frontier set that contains the current search frontiers and a closed set that includes all previously searched nodes. In our maze example, each node represents an empty grid cell. The algorithm calculates a heuristic value and a cost from the start for each node. Which node to search next is determined by the contents of the frontier and closed sets, along with the heuristic and cost from start values. The execution trace of A is collected by tracking all operations of adding nodes to the frontier and closed sets, along with their heuristic and cost values. This trace is structured so that the next token can be accurately predicted from any given prefix of the trace. For the maze datasets, A** uses the Manhattan distance to the goal as a heuristic. In Sokoban, A** matches each box to the nearest dock and calculates the sum of the Manhattan distances between each box-dock pair. For our experiments, we generate two types of token sequences: a search-augmented sequence, which includes the A** execution trace and the optimal plan, and a solution-only sequence, which omits the A** execution trace and only contains the optimal plan. These sequences are synthetically generated using a special vocabulary, and every model is trained from scratch without using any natural language dataset. This ensures that the models are specifically trained to predict sequences that outline optimal plans for various planning tasks. After training, we evaluate the model's output to check if it contains a correct and optimal solution plan. Section Summary. In this section, we focus on improving the reasoning capability embedded in a transformer's weights by using a search dynamics bootstrapping method to generalize towards more efficient search patterns. Unlike existing methods that treat neural network models as black boxes, we incorporate how a planning algorithm arrives at a final result into transformer models, demonstrating that transformers can not only imitate a symbolic planning algorithm but also improve past the algorithm they were initially trained on via fine-tuning. Our approach, SearchFormer, uses a general transformer architecture with long contexts and positional embeddings to predict optimal plans, showing promising results in solving complex planning tasks such as maze navigation and Sokoban puzzles. Section: Training a transformer model. In this section, we discuss how we go about training a transformer model. To do this, we first create a random collection of planning tasks along with their corresponding sequences of tokens. In our dataset, every task is distinct, ensuring that the test set does not include any tasks that are found in the training set. This means, for instance, a maze task found in the training dataset will not appear in the test dataset, ensuring no repetitions. Through this experimental setup, we aim to explore the capabilities of transformers in solving planning tasks. We train the transformer model to mimic the computation steps of the A** algorithm by including intermediate computation steps in the training process. This method is akin to procedure cloning, where the neural network learns not just from input-output pairs, in our case, the task prompts and the optimal plans, but also from examples showing the process of solving a task. In our experiments, we modify the encoder-decoder T5 architecture to include rotary position embeddings, ROP. The encoder is tasked with processing the prompt part of a training sequence, while the decoder is responsible for processing sequences formatted as a trace and plan to train a search-augmented model, or just a plan for training a solution-only model. Depending on the variant of the model, we aim to maximize the similarity between the sequences generated by the decoder and those sampled from the training dataset, using a method known as cross-entropy. We calculate gradient updates through a technique called teacher forcing, with more detailed information on our optimization approach available in the appendix. Moving beyond simply imitating algorithms through search dynamics bootstrapping, we introduce a method to decrease the number of search steps a search-augmented model needs to generate during inference. Initially, a search-augmented model is trained to mimic the search behavior of our A** algorithm, which is non-deterministic in nature. This means it randomly decides between costs that are equal and randomizes the order of expanding child nodes. This approach doesn't reduce the efficiency of the A** search but changes the order in which nodes are explored while still adhering to A**'s heuristic and cost calculations. By using a non-deterministic approach, we introduce variability in the length of each execution trace, allowing the model to approximate the distribution of the training sequences more closely. After training the model to imitate the non-deterministic A** search dynamics, we use it to create a new training dataset with shorter token sequences. This is done by generating multiple token sequences for each training prompt with the trained model, but only using sequences that end in an optimal plan and are shorter than those in the original dataset. If a generated sequence doesn't meet these criteria, we revert to using the original sequence. The search-augmented model is then fine-tuned on this new dataset of shorter sequences, which we refer to as the search-former. This process can be repeated, further fine-tuning the search-former on increasingly shorter sequence datasets, which we demonstrate reduces the number of search steps needed during inference and improves performance. At this stage, the search-former no longer simply imitates a** search but has discovered a new method for solving planning problems with fewer search steps. In our experiments, we generate sequence datasets using both deterministic and non-deterministic variants of a** search. For the deterministic dataset, sequences are generated by executing a** in a predictable manner, meaning the order of child nodes and the breaking of cost ties are predetermined. This results in a unique optimal plan and execution trace for each task prompt, simplifying the training of a transformer model since it only needs to learn the next token in the sequence. Evaluating such a model is straightforward as the generated token sequences must exactly match those produced by A. On the other hand, to diversify our dataset and include different search sequences, we generate sequences using a non-deterministic approach to a** search. This involves randomly shuffling the order of child node expansion and breaking cost ties randomly. As a result, the generated sequences and the resulting plans, while still optimal, vary between executions. This approach does not compromise the efficiency of a** search but forces our implementation to explore different search sequences. Other strategies for randomization could be explored in future work but are beyond the scope of this paper. Section Summary. In this section, we train a transformer model by generating planning tasks and token sequences, ensuring each task is unique between the training and test sets. By training the model to imitate the computation of the a** algorithm, we use a search-augmented model to reduce search steps during inference. This approach, called search-former, discovers new ways to solve planning problems efficiently by generating shorter token sequences through a non-deterministic a** implementation. Section: Statistics. In this section, we delve into the statistical analysis and evaluation criteria used in our study, focusing on the Sokoban dataset and various maze datasets. We observe that the length of the execution traces generated by the a** algorithm increases with the size of each maze's grid. Specifically, in Sokoban, which has the largest state space among the tasks we examined, the execution traces are notably longer. However, it's interesting to note that the solution plans for Sokoban are among the shortest. When evaluating the models, we consider three possible outcomes for each task: an optimal plan, a correct but suboptimal plan, or an invalid plan. To determine if a plan is valid, we check not only if the final solution sequence is feasible but also if it adheres to the correct output format. Models that augment their solutions with search sequences must produce an output in the format of a trace followed by a plan, while models that provide solutions only must output a plan format. Any generated sequences that don't follow these rules or fail to predict an end-of-sequence token are excluded from our analysis. To assess the optimality of the output plans, we employ three different criteria. The first is the exact match criterion, where a sequence generated by a model is considered correct if it exactly matches the output from the deterministic a** algorithm. This criterion is specifically used to evaluate how well a model can clone the deterministic a** output. The second criterion, any optimal 64, involves sampling 64 responses from a model for each task, checking if any of these plans are both feasible and optimal, regardless of the generated trace part. The third measure we use is the success weighted by cost (SWC) score, which evaluates how close the cost of the best predicted correct plan is to the optimal plan cost, averaged across all test tasks and weighted by whether a correct plan was found. Furthermore, we measure the length of the search dynamics in terms of token numbers, using two criteria: the average on optimal length and the improved length ratio of search dynamics (ILR) score. The ILR score compares the length of the shortest generated search dynamics sequence to the A** token sequence length, averaged across all tasks where either an optimal or a correct plan was found. In our first set of experiments, we train encoder-decoder transformer models to predict optimal plans for 30 by 30 mazes, varying the training dataset size and model size. We evaluate each model's performance using the exact match criterion. Our findings show that, especially in scenarios with limited training data, search-augmented models significantly outperform solution-only models, despite the former needing to generate sequences that are on average more than 10 times longer. This is a surprising result, particularly noting that even the smallest search-augmented model with 15 million parameters outperforms much larger solution-only models with 175 million parameters. Section Summary. In this section, we present an overview of the token sequence lengths used for different model types on the Sokoban and maze datasets, where the length of generated execution traces increases with maze grid size. We evaluate model performance based on criteria such as plan optimality and search dynamics length, using measures like SWC score and ILR ratio to assess how well models generate optimal plans and search efficiently compared to deterministic A***. The results show that even with longer sequences generated by search-augmented models, they outperform solution-only models, indicating the effectiveness of incorporating search dynamics in planning tasks. Section. Evaluation with the Any Optimal 64 criterion. In this section, we discuss how we evaluate our models using a criterion we call Any Optimal 64. When our models are trained with data from the non-deterministic A** algorithm, it's possible to have several different but equally optimal paths for a single task. In real-world applications, the goal is usually to find just one viable plan, making the Any Optimal 64 metric a more fitting measure. This metric is more forgiving than exact match criteria because to earn a point, only one of the generated responses needs to be correct. We've graphed the performance of our models on the test set using the Any Optimal 64 metric as it relates to the amount of non-deterministic A** training data they were exposed to. The results show a clear trend. Even our smallest models enhanced with search capabilities outperform those that rely solely on solutions, especially when the amount of training data is limited. Interestingly, the size of the model only really matters when the training dataset is very small, like 50,000 sequences. For larger datasets, the difference in performance between model sizes isn't significant. Adding more parameters to the models that only provide solutions doesn't notably boost their performance in scenarios with little data. We also looked at how the difficulty of a task affects model performance. We used maze size as a proxy for difficulty, assuming that larger mazes require more complex solutions. For smaller, 10 by 10 mazes, models that only provide solutions nearly matched the performance of those with search capabilities. However, as the mazes got bigger and the tasks more challenging, the performance of the solution-only models dropped sharply. In contrast, our search-augmented models maintained high accuracy levels, even with the smallest model size. An appendix in our paper offers a detailed comparison across all maze sizes, reinforcing that while solution-only models can learn to predict an optimal plan with enough diverse training data, search-augmented models are superior in data-scarce situations and scale better with task difficulty. This is because they can perform additional computations on demand during inference, controlling the search dynamics to derive an optimal plan, whereas solution-only models must rely on direct correlations learned during training, which can be unreliable. To see if these findings hold in more complex scenarios, we generated a dataset for Sokoban puzzles using non-deterministic A** traces. Similar to our findings with mazes, the search-augmented models outperformed the solution-only models, even when the latter had significantly more parameters. This confirms that our observations are not limited to a single task type or tokenization method. Lastly, we explored how to further improve the efficiency of search-augmented models through a process we call bootstrapping. Starting with a small model trained on Sokoban puzzles, we generated new, shorter training sequences that still contained optimal plans. By iteratively fine-tuning our model on these increasingly concise datasets, we developed what we call the search-former model. This model was able to generate search sequences that were, on average, 26.8% shorter than those produced by the A** search, showing that it found a more efficient planning method. Notably, the final search-former model was not only more efficient but also performed comparably to much larger models trained only to predict solutions. Our fine-tuning process significantly reduced the rate of incorrect and non-optimal solutions, demonstrating the potential of our approach to improve planning efficiency and accuracy in complex tasks. Section Summary. In this section, we evaluate the models using the any optimal 64 criterion, which is more suitable for scenarios where there are multiple optimal paths for a task. We observe that search-augmented models outperform solution-only models, especially for small training sets, as they can adapt their search dynamics during inference to find optimal plans efficiently. Additionally, by iteratively improving the search-augmented model through bootstrapping, we achieve a search-former model that generates shorter search sequences, leading to more efficient planning even for complex tasks like Sokoban puzzles. Section: Reduced length of search dynamics with search-former. In this section, we delve into how the search-augmented models, including search-former, have enhanced the efficiency of generating search steps to arrive at a correct plan. Our analysis here is distinct from the improvements showcased in previous figures, as we concentrate on comparing the length of the search sequences produced by each model to those generated by the A** search algorithm. We employ the improved length ratio (ILR) measure for this comparison, which helps us understand the extent of improvement in search efficiency. Our findings, detailed in the corresponding table, reveal that each iteration of enhancement on the search-former model leads to the creation of increasingly shorter execution traces. This progression results in higher ILR scores, indicating a more efficient search process. On the other hand, the ILR scores for the two search-augmented models are slightly less than 1. This suggests that these models, while effective, still perform a marginally higher number of search steps compared to the A** search algorithm. However, when we fine-tune the models, the ILR score surpasses 1, signifying a more efficient search dynamic, especially in scenarios that require the formulation of optimal plans. To put it into perspective, the search dynamics of the A** search are approximately 34.3% longer than those produced by the search-former after it has undergone 3 steps of fine-tuning. For those interested in a deeper dive into the performance characteristics of these models, we have provided more detailed information in the appendix. This analysis underscores the potential of search-former and similar models to streamline the search process, making it quicker and more efficient in finding the correct plan.